Hi, myself Dr. Avik Pradhan, Assistant Professor, Department of Mathematics, School of Basic and Applied Sciences, Adamas University. In this lecture, we are going to discuss about basics of probability theory. In this lecture series, in this unit, we are going to discuss about basics of set theory, and then we'll talk about the definitions of probability. We'll talk about the classical definition, statistical definition, and subjective probability and axiomatic definition. And then we'll go for the some basic theorems of probability, and then we'll go for the conditional probability, independentness of the events, and then we'll go for the Bayes theorem. So let us start with the basic of set theory. Okay. So what is a set? A set is a well-defined collection. Now, collection means it's a group. So what do you mean by well-defined? So let me take an example and discuss about this. Suppose I'm taking a group or collection as suppose X is equal to, I'm taking 1, 2, 3, and I'm taking another group or collection like 1, A, then I'm taking suppose 5. Okay. Now in the first X we have 3 elements. Each component of the collection are called elements of the set. So in the first group or the collection we have 3 numbers 1, 2, 3. Then they are numbered. They are having the property that they are representing some number, natural number. So these actually define, they are well-defined objects. Now, if I think about the second group, there you can see I have 1, which is a number. I have A. About A, we do not know about anything. It's a symbol. A is a, like if I think about this thing as a letter, I can think this as a letter. I can think this as a variable. I can think this as a number. Means if I put A equal to suppose 2, it becomes a number. So it could be anything. And 5 is again a number. So in this collection, I have 2 numbers, 1 and 5, whereas there is some ambiguity about this A. We do not know what kind of thing is this A represents. So it could be a symbol, it could be a letter, it could be anything like any some kind of ambiguity or vagueness is there in this definition of A. So all the elements of this collection are not well defined. So Y is not a set. It's not a set here. This Y is not a set, whereas this X is a set. So is it clear that A is a set is a collection of well-defined objects. Well-definedness means the objects are having same properties. Okay. Now, once we know about the set, then we can define some operations on the sets. But before going to the operations of the set, we need to first look into the equality of the sets. Suppose I am having 2 sets X, which is equal to suppose 1, 2, and 3. I have another set Y, which is equal to suppose A, B, and C. When these 2 sets X and Y will be called as a equal sets. Okay, so here also Y will be a set if A, B, and C have same properties, they are well defined. Then only we can say that this Y is a set. Okay, so before going to this equality of the set, we need to talk about the subset notation. Okay, so what do you mean by a subset? Here I have given that if every element of a set A, if every element of a set A belongs to the set B, that means if X is an element of the set A, then it must contains in B if A is a subset of B. That means X belongs to A implies that X belongs to B. Then only we can write that A is a subset of B. And if we find that there is some element in B which does not belongs to A, then we call that A is a proper subset of B. Let me take an example here. Suppose I have A equal to uh, set of natural numbers. Let me take. So A is equal to all X such that X belongs to natural number. So it's A is a natural number set. And let me take B is equal to suppose real number set. Then obviously set all the elements or all the natural number are real number. So A will be a subset of B. Now there are numbers, for example, suppose X is equal to half. It's not a real number, but this number belongs to, X is equal to half, which is a real number, but not a natural number. So this X does not belongs to A, but X belongs to B, which implies that means A is a proper subset of B. So a subset means a set which is contained in another set. Suppose if I say that A is a subset of B, then A is contained in B. And if I say that A is a proper subset of B, then there exists an element in B which does not belongs to A, and A is also contained in B. Okay, so then we say that the set A is a subset of B if A contained in B, and it will be a proper subset if there exists some element in B which does not belongs to A, and A is a subset of B. Then it is called the proper subset. Now, two sets A and B are said to be identical or equal if both the sets are subset of the each other. That means if I have A is a subset of B and B is a subset of A, then we say that A and B are equal. Okay. So if I want to prove that two sets are identical, then we have to show that both the sets are subset of each other. So A equal to B if and only A is a subset of B and B is a subset of B. So obviously A and B should have equal number of elements. Now here I should mention one thing that the number of element of a set represent the cardinality of the set. That means how many elements are there in that set that represent the cardinality of the set. For example, if I take A equal to suppose 1, 3, 5, 4, so in that case I'll have cardinality of A, it represented by mod of A, which is equal to 4 here. That means 4 elements are there in this set. Okay. If I have a discrete set or if I have a countable set, we can very easily find the cardinality of the set. But if I have an infinite set, means infinite number of or uncountable set, then it is very difficult to find the cardinality. Okay. So let us go to the next topic, which is the operations on A. Okay. Before going to these operations on A, we need to know two more things here, which are usually used to define everything in the set theory. One is null set. What do you mean by the null set? Null set means the set which does not contain any element. Okay. That means if I means null set is there is no element in the set, and universal set means the set which contains all the objects related to the set, including itself. So universal set is like, if I think about the number system, in the real number is a universal set, and in that case, if I take any set like a equal to 1 2 3 4 5 6, it is a subset of the universal set. So whenever we talk about the universal set represented to some sets which are related. Suppose if I consider set of numbers, in that case we can think about the real numbers as the universal set. If I have the problems where the set deals with only the real numbers, then we can think about the real number set, that is script R, as the universal set. That this set can be considered as the universal set in that case. Okay. So these two sets, null set and universal set, are very important here. So here I have mentioned a few remarks here. First of all, that every set is a subset of itself, because we know that if I consider A is subset of A itself, and A is a subset of A itself, then we can write A is equal to A. So that means basically every set is the subset of other one, means they are subset to itself. The second thing says that an empty set is a subset of every set. That means if I think about the empty set is the set which does not contains any element. So if I think about the any set A, suppose, then I have suppose elements 1 2 3, then 5, which is the null set, which does not contain an element, is always a subset of A. Okay, so that is the second remark I have made. And third remark is that a set containing only one element is conceptually distinct from the element itself. What does that mean? That means if I consider suppose A equal to singleton 1, that is a set. It is a set, but 1 is a number. So basically, if I think about these two things, they are different. That means this A representing a singleton set, it's a collection, the collection which contains only one element, that is 1. But if I think about this one, it is the number 1, which is different from the set. Set means collection, here it is a number itself. Okay, so these two things are different. Now, if I think about the last remark, whatever I mentioned, here in our probability theory, we will actually think about the sample space. We will talk about the sample space, which should be defined in advance. Okay, and we should be concerned only with the subset of that given set. So here I should mention one thing. If I have a discrete set, for example, suppose A, which is equal to suppose 1 2 and 3, if I have these elements, then in our probability theory we actually concerned with the subsets of this set. Now what could be the possible subsets of this A? As I already mentioned in the second remark, that 5, that is the null set, is a subset of A. Now, if I consider singleton set of these elements, so singleton 1, singleton 2, singleton 3, they all are subsets of A. Now, if I think about two elements at a time, like 1 3, then if I consider 2 3, so these elements and A itself, they all are subset of A. So how many elements are there? 1 2 3 4 5 6 7 8. So there are 8 possible subsets, 8 subsets of A. There are 8 possible subsets of A. Now if I think about more generalization, so if I have 3 elements in the set, that is the cardinality of the set is equal to 3, then we are getting 2 to the power 3. That means 8 number of possible subset in of A. So similarly, if I have n number of elements in the set, then we will have 2 to the power n number of subsets for that set. Okay. So now, if I consider the collection of these sets, if I consider the collection of these sets, collection of all the subsets of a given set, then it is called the power set of that. We will have some, I mean, so we'll talk about these sets especially in the probability theory. It have a very important role in the development of the probability theory. So we'll look into this thing later on again. Okay. So till now, whatever we have discussed, that is the basic definition of the probability. Sorry, basic definition of set, and then we talked about null set, universal set, and some remark on that we have made subset and equality of the set. Now we'll go for the operations on set. So basically, there are basic few operations are there on the set. First of them is the union. So there are union, intersection, complement, relative difference, and symmetric difference of the sets. So if I think about the union, union is like we are accumulating everything. Okay. So if I consider two sets A and B, then the union of those two sets A and B will be the collection of all x such that x belongs to A or x belongs to B. So, for example, if I take A is equal to suppose uh, A, B, C, three letters we are considering, and B is equal to suppose I am taking 4 minus 3, 2. Then what will be A union B? Here is B. So A union B is equal to, this will be uh, A, B, C, 4 minus 3, 2. That means all the elements from A and B. Now here if I consider, instead of taking this A as ABC, let me take some other values here. So suppose 1, 2, 3, 4, 5, 6. So in that case, this union set will be like 1, 2, 3, 4, 5, 6, and minus 3. So you can say A union B will be all the elements which belongs to A or B. So 1, 2, 3, 4, 5, 6 all belongs to A, and here in B 2 and 4 are there, so they are repeating, so it is not to consider that thing. But if I look into this B, minus 3 is another element, so which is not belongs to A, so I consider minus 3 in this set. So union B becomes 1, 2, 3, 4, 5, 6 and minus 3. So this would be the set which is union of A and B. Okay. So now let us go for the second operation, which is the intersection. So I will come back to this point again. I will discuss this thing in terms of the Venn diagram. We have a concept of Venn diagram also in the set theory to geometrically represent the things. So now let us go for the intersection. Intersection is set of or collection of all the elements x such that x belongs to A and x belongs to B. That means we consider those elements which are common in both the sets. So x belongs to A and x belongs to B. And in this union, you have seen the word or, and in the intersection, we have the word and. So whenever linguistically, if I mention something as and in the probability theory, we consider that as a intersection of the events. So if I look into this same example, then A intersection B will be the elements which belongs to A as well as in B. So if I look, I can see there are two elements which are common in both the sets. They are 2 and 4. So we consider that intersection of A and B will be these two elements. They are common. Okay. Now, if I think about the complement of the set, now if I look into this A set, A represent the positive numbers, positive natural numbers, 1, 2, 3, 4, 5, 6. 6 natural numbers are there. Now, if I consider the universal set, which is U, I'm writing as U equal to set of natural numbers. Then this A complement will be the set of natural numbers minus the set A. So that means complement means the set of or the collection of all the elements X which does not belongs to A. So where then from where this X belongs to, then it must be from the universal set. So as I already mentioned in the last slide, that what is a universal set? Universal set is the set of all the elements related to a set. So if I consider this A contains some integers. So I can think, or rather I should say that A contains the natural numbers. So if I consider this set A, then if we want to find the complement of this A, then I should consider the natural number set as the universal set. So natural number set is the universal set. So A complement will be the elements which does not belongs to A but contains in universal set, which is natural number set. So this A complement will be the natural numbers excluding 1, 2, 3, 4, 5, and 6. So that will give you the complement set, complementary set. Okay. So the next concept in this operations on set is the concept of relative difference. So now what is the relative difference? Relative difference actually already we have seen in this definition of uh, complement of a set. So relative difference is nothing but uh, the difference of two sets. If I think about in this manner. Suppose I have two sets A and B, then A minus B are those elements which contains only in E but not in B. So X belongs to A but X does not belongs to B. So if we look into this definition properly, I can see it is very much related to the complement set. Suppose I have a means if we have seen A complement is equal to A complement is equal to universal set minus A. That means all the elements which belongs to the universal set but does not belongs to A. Similarly, A minus B, if I consider A minus B means like all the elements of A which does not belongs to B. So if I consider two sets, let me take A is equal to suppose 1, 3, 5, 7. Suppose A equal to this, B equal to suppose -1, 1, 5, 6. So what will be A minus B? A minus B is going to be all the elements which is not belongs to B but belongs to A. So if I look into this 1 belongs to B. So in A minus B, 1 should not be there. If I look into this 3 does not belongs to B. So I can take 3 in this set. 5 belongs to B. So I should not take 7 does not belongs to B. So this will be the element in this A minus B. So A minus B, if I think I can write this A minus B in some by using some other operations on the set also. I can think this A minus B as A intersection B complement. You can see what will be the B complement. B complement will be the elements which does not belongs to B and belongs to the universal set. So if I consider that A intersection that universal set, it becomes A itself. So A minus B will give you this element. So I can always write that A minus B is equal to A intersection B complement. So already I have defined the what do you mean by intersection, and I have already defined about the complement. So I can club these two things to define the relative difference. So here I have mentioned A minus B. Similarly, you can define B minus A also. So B minus A will be set of all x such that x belongs to B, but x does not belongs to A. So if I look into this example, I can find this set will be equal to like -1. It belongs to B but does not belongs to A. It will be 5, 1 is there, 5 is there, so 6 will be there in this B minus A. So they are called relative difference. So A minus B is all those elements of A which does not belongs to B. B minus A are all those elements of B which does not belongs to A. Okay, so let us go to the next definition. Is this. So the next definition is related to the symmetric difference. Symmetric difference is nothing but which is it's related to the relative difference also. Symmetric difference is the union of the relative differences. So for example, if I consider A equal to, let me take 1, 2, 3, 4, B equal to suppose -1, 1, 3, 5, then A minus B is equal to a set of all elements of A which does not belongs to B. So I can see there 2 and 4. B minus A which is equal to B minus A will be -1 and 5. So A symmetric difference B will be equal to union of these two sets. So union of -1, 5. So this will be equal to -1, 2, 4 and 5. Now, just look into one thing, that what is the A minus, sorry, A intersection B? A intersection B are the common elements, that is 1 and 3. Now, what is A union B? If I let me take it here, what is A union B? A union B will be equal to like it's -1, 1, 2, 3, 4 and 5. Okay, so if you look into these three things, that is A union B, A intersection B, and A symmetric difference B, there is a relationship. You can see that A union B is nothing but union of symmetric difference of A and B and the set which is A intersection B. So I can write this thing A uh, A symmetric difference P is equal to A union B, okay, A union B minus A intersection. Okay, so I can just delete those element of A intersection B, and whatever the leftover part, that will be the asymmetric difference. Okay, so we have seen just the operations on set by using some examples. Now we'll try to understand these operations on the set by using the geometrical concept. So here, which is called actually the Venn diagram concept. So I'm taking the set which is universal set. So these I'm representing by universal set capital U. Now I have two sets which is A and